Hello and welcome. Today, we're venturing into the vast, dark reaches of our own solar system. While we know our planetary neighbors fairly well, there's still so much out there waiting to be found. From tiny asteroids and comets whizzing through space, to the tantalizing possibility of a large, unseen world like Planet 9, the hunt is on. But how exactly do scientists search for these hidden cosmic residents? It relies on incredibly sophisticated ways of looking at the sky and powerful methods for sifting through mountains of data. The main strategy today involves casting a really wide net using wide-field surveys. Instead of pointing a telescope at one known object, powerful instruments repeatedly scan huge sections of the night sky. One key technique is wide-field imaging. Telescopes with massive cameras take pictures covering large areas. By comparing images taken hours, days, or even weeks apart, astronomers can spot faint points of light that have moved against the backdrop of distant, fixed stars. That movement is the giveaway sign of something orbiting our sun. Telescopes like Pan-STARRS, the Zwicky Transient Facility, Hubble, and even the James Webb Space Telescope are all involved. And the upcoming Vera C. Rubin Observatory is set to completely revolutionize this approach. Another clever method is occultation monitoring. This involves watching thousands, even millions of stars, looking for incredibly brief, tiny dips in their brightness. These dips happen if a solar system object, maybe a small body way out in the Kuiper belt, passes directly between us and the star, momentarily blocking its light. It's a great way to find objects that are too faint or too far away to see directly by reflected sunlight. And sometimes, it's not about reflected light, but about heat. Some telescopes, especially space-based ones like WISE, observe in infrared light. This lets them detect the faint heat signature emitted by objects themselves. This is really useful for finding very dark objects, or those incredibly far from the sun, where sunlight is weak. Now, scanning the sky like this generates an unbelievable amount of data. Terabytes every single night, potentially containing millions of light sources. Finding a tiny moving object in all that is like finding a needle in a cosmic haystack. That's where sophisticated data analysis comes in. Automated software pipelines are essential. These algorithms automatically process the images, comparing them to spot movement, identifying potential candidates, and filtering out false alarms like cosmic rays or satellite trails. Once a potential moving object is flagged in several images, the next step is calculating its preliminary orbit. Using complex math, scientists figure out its path around the sun. This helps predict where it will be next and confirms whether it's a genuinely new discovery or just something we already knew about. Artificial intelligence and machine learning are also playing a bigger role. I can be trained to spot the very subtle signs of moving objects hidden within noisy data, sometimes catching things traditional methods might miss. And it's not just machines. Citizen science projects, like Backyard World's Planet 9, enlist help from the public. Volunteers look through survey images, and human eyes are still fantastic at pattern recognition, often spotting faint or slow-moving objects that automated systems might overlook. Citizen scientists have already contributed to finding numerous brown dwarfs and potential solar system objects. Beyond just spotting objects directly, astronomers also study the orbits of known distant bodies, like those beyond Neptune. If many of these objects have strangely aligned or clustered orbits, it could be a sign that a large, unseen planet's gravity is pulling on them. This dynamical analysis is the main reason scientists hypothesize the existence of Planet 9. Of course, finding these faint, distant members of our solar system is incredibly difficult. They move slowly across the sky and are extremely dim. Telling them apart from background noise and detector glitches requires painstaking work. But the future looks bright. Upcoming surveys, especially the Legacy Survey of Space and Time with the Rubin Observatory, will provide data deeper and more comprehensive than ever before. Combined with ever-improving computing power and smarter algorithms, our chances of finding new worlds, big and small, are better than ever. The search continues, constantly pushing the limits of our technology to uncover the remaining hidden residents of our cosmic neighborhood and perhaps rewrite our understanding of how our solar system came to be. Thanks for listening.